Bismillah ar-Rahman ar-Rahim. Today we will discuss gas chromatography and mass spectrometry. There are two versatile techniques. They identify or measure the concentration of anesthetic agents or other gases present in the mixture. They are commonly employed in laboratories. First of all, the gas chromatography. Chromatography literally means write in color. So as an example, we will see in case we have a dye and we pour this dye in a supportive media as calcium carbonate, as we can see, the constituents of the dye are being separated into items, as you can see, and then eventually they are released to a cup according to the solubility in this supportive media. This is a resemble of what we will show later on by the monitor we will use. This supportive media are similar, and of course, instead of having cup releasing the constituents, we have what we call the detector. The pouring process is called the mobile phase, and the supportive media where the components are being fixed and then released later on, or later on are called it's called the stationary phase. So we have two phases. Regarding the monitor that we will show, as we can see, the column where we have the supportive media is made of silica alumina. These particles are coated with silicon oil. This is the first thing. Second thing is that the mixture being analyzed, injected into a port, as you can see, in the system, where the mobile phase is carrying this mixture through a flow meter to the supportive media, which is made of a long glass coil to improve the proper separation of the constituents of this mixture. Of course, each of the components are being kept for a period according to the difference of solubility between the mobile and the stationary phase, and they begin to be released one after other to be detected by the detector and going to a recorder. Of course, this system is controlled thermostatically by a thermometer to keep it in a special temperature. And as we said, it is a long coiled glass tube to make the separation much better. The detectors, we have three types of detectors. First of all, what we call the flame ionizing detector. What's the meaning of that? That we are creating a flame made of air and hydrogen, and then this flame is ionized. Whenever I apply two electrodes or creating a potential across this flame around 150 volt, creating particles. So whenever a halogenated component is being entered to this detector, it will change the current according to the ionization with which it occurs. See, the second thing is the casserometer. The casserometer is made of a heated wire where its resistance is going to be affected, of course, by the current or by the inorganic materials passing. It is specific for inorganic materials as, of course, oxygen, nitrogen. So this casserometer will decrease the resistance of this wire according to the gas passing by it. The last one is what we call the capture electron detector, where a cathode is being used to create electrons going from the cathode to anode. This electrons are being captured by the organic material going through it. This capture will, of course, affect the current. Accordingly, will give us a hint about this type of gas entering the system. the disadvantage of the chromatography that you have to have preliminary knowledge about the constituents of the mixture. You see, this is the point. The time taking for the detector to identify the type of the gas is called the retention time. As you can see from this figure, suppose after 4 minutes we have a peak that appears. We know from calibration means that there are figures denoting that after 5 minutes, suppose what will be realized is, suppose, calcium, or I'm sorry, oxygen. So we can say that this height is also oxygen, and we can compare the two heights, and accordingly we can know the amount of oxygen present. And these are the other calibration for different constituents of the mixture. Of course, the sample is being introduced through a rubber septum, as you can see, or a special valve whenever we use a liquid directly, or of course whenever I have a liquid through this port is being heated to be vaporized and then shifted to a vapor so it can be detected. Of course, the clinical advantage of it can, of course, estimate the volatile anesthetic agent amount up to very trace levels. It is versatile. It can measure liquid and gas. The bad thing about it that you cannot give a continuous analysis, and it is cumbersome. It is difficult to be used in the theater, and you must have preliminary knowledge about the constituents of the mixture. Now we come to the mass spectrometer. The mass spectrometer, as we can see, is made of a chamber. The chamber contains the constituents of the mixture, and through a pump is being released through an opening to a chamber where there is a potential developed a cathode releasing electrons. These molecules, we call it, whenever they are released, they are called molecular leak. Is being leaked through an opening, and then they are ionized through this cathode and anode. So the ionized components passed by what we call an accelerating and focusing plate, something turning very fast to control accordingly, and then we create beams. These beams are reflected through a magnetic field. Of course, it depends upon the mass of the molecule. Whenever the mass has a low figure, it of course is easy to be deflected. As you can see, we have 3 forms of different ionized being deflected from the magnetic field, and then we have a detector. We can guide this beam accordingly to go to the detector according to my needs. So I adjust this focusing and accelerating plate to choose, suppose, the one in the middle to go to specifically to this detector. You see, this is the method how to control or measure the components of the mixture. And instead of this magnetic field, we can have 4 poles electrically charged. We call it a quadrupole mass spectrometer instead of this magnet, and it goes in the same way as the previous one. We have a molecular weight leak, and then we have a cathode and anode, an ionization, and then we have the controlling the volt of this rods to go to the specific to choose the specific beam where it will go to be recorded by identified and recorded by a detector. The last thing, of course, there are other methods to identify the vapors. We have the crystal of quartz. This crystal, whenever it is being electrified, it oscillates. You see, so whenever I put a coat of oil around it, and then I expose it to a vapor, this vapor will be dissolved into this oil according to Henry's law. So it will change the oscillation, the frequency of how it will rotate. This change will make me identify the gas and knowing its concentration. The other thing, we can of course use the refractometers, as we said before, and we can use ultrasound speed through the vapor to change to notice the shift in the change of the frequency of the ultrasound to identify the gas. A Raman effect is based on the notification that whenever electromagnetic waves are exposed to molecules, these molecules either scatter this incident ray with an energy equaling the incident energy, or it can absorb it completely as CO2 absorbs infrared rays we mentioned before, or it can absorb a sort of this energy, some of it. You see, this is most probably what happens. You see, so this is this partial transfer of energy is called Raman effect. So Raman effect is made of special detectors. These detectors are 8 in figure. Now we are showing only 2 of them. This detector is made of a filter. This filter is specific for the gas in concern. You see, each gas absorbs the infrared rays of a special frequency and reflects it in a special frequency. So accordingly, we can identify. So we have the detector made of a filter for the specific wavelengths, and we have what we call a photo detector. This photo detector convert the incident rays to electrical signal for measuring and processing. You see, the filters are specific for the different types of gas, as we can see, and it is the most nice thing about it that the carbon hydrogen bond present in inhalation anesthetics is very strong as an identifying the halogenated agent. You see, so we use it to identify the type of anesthetic gas present. But I'm afraid that whenever there are different or three inhalation anesthetic present in this mixture, it may give me inaccuracy. So it's preferable to have only one. Of course, there is a pump to degrade to remove all the degradation products. You know, this heat present by the laser. Of course, we have to have a beam made of laser. This laser is made of helium. Because this effect is very weak, you see, so we must have a strong source of light. This strong source of light can cause degradation of the components, releasing products. So you must remove it by a pump. On the other hand, we must have a method to dehydrate the mixture. Of course, as you can see, we pass air through the chamber. We have 2 mirrors. And then the detectors ought to be perpendicular to the course of the beam, because it is a very weak response. So it will be more accurate whenever it's perpendicular to the course of the beam. I hope that I accomplished my missions, and I'm sorry for my mistakes. والسلام عليكم ورحمة الله وبركاته.